I want you to think about the last time you learned a new math concept.
Oh, that's a stressful thought for a lot of people.
Right, like maybe it was back in high school and you're just staring at this chalkboard covered in equations
Mm-hmm.
and you're feeling like you're trying to decipher some ancient alien language or something.
Absolutely.
Because we we almost always talk about math like it's this incredibly abstract foreign invention, like it's a rigid set of rules that we humans somehow forced our squishy primate brains to understand.
Right, like we had to conquer our own biology to get it.
Exactly. But what if that is entirely backwards? What if
Yeah.
you didn't actually, learn math at all? What if you and your ancestors stretching back millions of years, what if you actually embodied it first?
This is the big question.
Yeah, so welcome to today's deep dive. We are looking at this truly mind-bending visual and theoretical document today. It's titled The Geometry of Intuition.
And it is a phenomenal piece of work, honestly. I mean, the central thesis, it just completely flips our standard understanding of, well, of human intelligence and technological progress.
It really does.
It basically makes the case that we've been looking at the history of mathematics through the wrong end of the telescope this whole time.
Right, because the mission of this deep dive is to explore the premise that our biology literally wrote the foundation for modern machine learning algorithms.
Exactly.
Like the algorithms powering the artificial intelligence revolution aren't just, clever code we invented out of thin air.
No, not at all.
They're a direct translation of human evolution. So we're going to explore this concept that the source material calls proto-math. Okay, let's unpack this.
Yeah, and that's a perfect place to start, I think, because it really sets the baseline for everything that follows.
Right.
The core argument here is that mathematics is not an invention. It is a biological memory.
A biological memory. I love that.
Right. Like long before a human being ever scratched an equation for, say, linear algebra into a clay tablet or chalkboard, our bodies and our brains were intuitively navigating the physical world using this proto-math. So formal mathematics, the symbols, the matrices, all those equations, it's simply the retroactive, precise language for the order our biology has instinctively felt for millions of years.
Yeah, that phrase, retroactive language, it's like we spent millennia feeling the rhythm of a song in our chest,
Yeah, exactly.
And only recently did we finally figure out how to, write down the sheet music for it.
That's a great way to put it.
And to understand how our biology wrote that sheet music, how it wrote the algorithms we use today, we kind of have to start at the very beginning of human movement.
Yes.
We have to talk about our relationship with gravity.
Right, because gravity is essentially our first math teacher.
Okay.
And the classroom for this lesson is the vestibular coordinate system.
The inner ear.
Exactly. Inside your inner ear, you have these three fluid-filled canals.
Yeah.
And it's not just the fact that they exist that's cool. It's their highly specific geometric arrangement.
Right.
They're positioned exactly orthogonally to one another.
Okay, wait, let's make sure we define that clearly for everyone listening. Orthogonally, we're talking about right angles, right?
Yeah,
Like exactly 90 degrees to one another, like the corner of a square.
Precisely. Yeah. You have an anterior canal,
Yeah.
a posterior canal, and a horizontal canal.
Okay.
And together they form this biological 3D coordinate system. An X, a Y, and a Z axis built right into the bone of your skull.
That's wild.
And this isn't just a random anatomical quirk, It is a perfectly calibrated sensor designed to maintain orthogonal balance against the constant, just unrelenting pull of gravity.
Yeah, and the source material has this incredibly striking image to illustrate this. It shows a toddler learning to walk.
Oh yeah, the toddler example is perfect.
Because if you've ever watched a toddler take those first steps, it's wobbly, it's chaotic. I mean, they're falling over every 2 seconds.
Constantly.
But think about what's actually happening under the hood. That toddler isn't consciously computing complex quark equations, right?
Right. They don't have a calculator out.
No. They aren't crunching numbers to find their center of mass. Instead, their nervous system is intuitively seeking out an orthogonal balance.
Yes.
They are desperately trying to find that exact 90-degree angle relative to the Earth.
Oh.
Because mathematically and physically, that right angle is the optimum point of stability to prevent a fall.
Exactly. Because bipedalism, walking on two legs, it's basically a controlled forward fall.
Right.
To pull it off, you are functioning as an inverted pendulum. That physical intuition of staying upright, of dynamically finding that perfect vertical alignment relative to the horizontal ground, that is our body's original linear algebra. You're doing math every time you stand up from a chair. You just You don't need the formulas to do it because millions of years of evolution have hardwired the computation right into your nervous system.
Wow. So this physical need for a 90-degree balance, it doesn't just stay isolated in our inner ear down there.
No, it doesn't.
It actually moves up the biological chain. It
Yeah.
dictates how our brain processes the visual world around us, which brings us to these things called grid cells.
Yeah, and what's fascinating here is that this is where the biological proto-math gets incredibly sophisticated.
Okay.
Human spatial awareness relies on a built-in grid-like coordinate system inside the brain, specifically in a region called the entorhinal cortex.
The entorhinal cortex.
Right, and when you walk into a room, these grid cells fire in a pattern that creates an internal map of your environment.
Hmm.
And here again, orthogonality, that perfect right angle. It acts as a biological noise filter.
Right, a noise filter. How does a right angle filter out noise in the brain?
So, in mathematics, particularly in linear algebra, orthogonal lines are what we call linearly independent.
Okay.
That means they absolutely do not interfere with one another.
Yeah.
If you think about a standard graph, movement along the x-axis tells you absolutely nothing about movement along the y-axis.
Right, they're completely separate.
Exactly. They're perfectly decoupled.
Mm-hmm.
And the brain perceives this mathematical lack of interference as absolute clarity.
Okay, I want to ground this in everyday experience for you listening because the document presents a really compelling aesthetic model here.
It really does.
Think about the intense, almost irrational satisfaction you get from straightening a crooked picture frame on a wall.
Oh, yeah.
Or conversely, think about the low-level anxiety of driving through a poorly designed parking lot.
Yeah.
You know the ones where the painted lines are diagonal, the lanes are intersecting at weird angles?
Oh, it's the worst.
Yeah, nothing lines up. According to this research, if you present the brain with chaotic, unaligned geometry, it results in a high cognitive load. Your brain is literally burning more glucose, working incredibly hard to parse unaligned data points. But if you present it with clean right angles, like a symmetric grid, it experiences cognitive relief.
Yeah, cognitive relief is the perfect term for it.
Hmm.
Because orthogonal lines, they don't require your brain to constantly calculate interference
Wow.
or overlap.
Right.
It is the cheapest, most efficient way for your neurons to process space.
But humans didn't just want to feel this mathematical relief inside their own heads, right?
No.
They wanted to project it outward into the chaotic world they lived in. Which leads us to ancient architecture.
Yes.
And I'll admit, when I was reading this part of the source, it really clicked for me. It points out that ancient builders in Egypt or Mesopotamia, I mean, they didn't have matrix algebra,
Definitely not.
but they were obsessed with mathematical perfection. They were building monumental structures using the simplest tools imaginable. Literally just a rock tied to a string, a plumb line, and knotted cords to make right triangles.
Right.
So how does the brain's desire for cognitive relief translate into perfectly engineered ancient architecture?
Well, it comes down to an unconscious drive to achieve something called isometry.
Isometry.
Yeah. Isometry is the mathematical property of preserving length and angle without distortion.
Okay.
Think about the natural world our ancestors lived in. It's full of chaos. Trees grow crooked, rivers wind unpredictably, the terrain is uneven.
Very messy.
Exactly. Those ancient builders, equipped with nothing but a plumb line dropping a perfect vertical line to the earth, they intuitively sought to manifest a permanent, undistorted order.
Wow.
Symmetrical orthogonal grids in architecture were a biological desire to defy natural chaos. They were externalizing that cognitive relief of the right angle and literally carving it into stone.
They were building the inner ear into their environment.
Basically, yeah.
Yeah, that is so profound. But the document points out that once our ancestors mastered the ground floor, once we could build these perfectly ordered isometric structures on the dirt, our biological intuition pushed us in a totally new mathematical direction.
Right. We looked up.
Exactly. We started building straight up. We discovered the z-axis.
Yeah, and if we connect this to the bigger picture,
Yeah.
you have to think about the 2D plane, the x and y axes on the ground, as the realm of survival.
Okay.
The ground is a crowded, highly competitive floor. It's where we forage, where we fight, where all our basic needs are met. It's messy down there.
Right.
But looking up and building vertically, it adds this strictly orthogonal z-axis.
And because that vertical line is strictly perpendicular to the ground, it is entirely mathematically independent of the ground's constraints.
Exactly.
I was marveling at this part of the text. It frames the simple act of erecting a monument or building a tower or even just looking up at the stars as an intuitive mathematical act.
It really is.
You're taking a system that is trapped in a flat 2D plane and extending it to 3D to create space for the future. The z-axis isn't just about physical height. It represents freedom, abstraction, and transcendence.
Yeah, it's dimensional expansion driven by pure instinct.
Right.
The logic of the vertical is the logic of expanding your mathematical space so you have room to breathe, room to think. You aren't just moving around the crowded game board anymore. You're hovering above it.
Okay, so what does this all mean?
Right.
I can hear you listening right now thinking, okay, this is deeply philosophical. We're talking about ancient builders, cognitive relief, toddlers learning to walk. But at the top of the show, you promised a connection to machine learning.
I did, yeah.
How on earth does a plumb line or a toddler's inner ear connect to the digital world?
Well, that is the crux of this entire deep dive. It's the bridge from biological instinct right to algorithmic stability.
Oh, yeah.
The exact same instincts that kept us balanced and allowed us to build cathedrals are the literal functional blueprints that make modern machine learning algorithms work.
Okay, so prove it to me. Connect the dots from the squishy human brain to the computer code.
Gladly. We need to introduce the golden rule of linear algebra, which is essentially the mathematical engine that drives machine learning.
Okay.
And that rule is orthogonality. In the formal math of data science, this perfection is often represented by a specific equation.
Lay on me.
Q transposed Q equals I.
Whoa, hold on. You just threw an algebra equation at me.
Yeah.
Assume I haven't looked at a math textbook in a decade.
Fair enough.
What is a transpose? What is Q? And why is it equaling I?
Yeah, let's break it down because it's beautiful once you see it.
Okay.
Let's start with the I.
Okay.
I stands for the identity matrix. You can think of the identity matrix as a pristine, perfect digital grid.
Got it.
It represents absolute clarity, where every single dimension is perfectly independent and there is zero overlapping noise. It's the mathematical equivalent of cognitive relief.
Okay, so I is the goal, a clean grid.
Exactly.
What about Q?
Q represents your data, specifically a matrix of data vectors. Now, the transpose, that little T you mentioned, it basically means flicking the matrix on its side.
Okay, flipping the data.
Right. So when you multiply a flipped version of your data by itself, Q transpose times Q, you are essentially testing how much the different dimensions of your data overlap or interfere with each other.
Ah, okay.
If Q transpose Q perfectly equals I, that perfect grid, it proves mathematically that your data has zero noise. Every piece of information is perfectly orthogonal, perfectly 90 degrees to everything else.
So Q transpose Q equals I is just the computer's way of finding the exact same 90-degree balance that the toddler is trying to find when they learn to stand up.
Precisely. The proto-math of our bodies is literally identical to the formal math that trains a neural network.
Here's where it gets really interesting. Let's get into the mechanics of this, because the document provides this incredible synthesis showing how specific machine learning algorithms literally mimic human behavior.
Yes, the 3 codex.
Right. Let's look at the first one, the Gram-Schmidt process, and this concept of basis extension. What is the biological link here?
The biological link is that human desire we just talked about to escape the 2D plane, striving upwards, building into the z-axis.
Okay.
In machine learning, you're often dealing with massive data sets with hundreds of thousands of variables, and a lot of those variables overlap. They bleed into each other.
Right. Data is messy.
Exactly. So the Gram-Schmidt algorithm builds a mathematical space step by step by extending into new dimensions, but it forces a strict rule.
What's the rule?
It ensures that every single new dimension, it adds points strictly straight up or orthogonally from all the previous ones.
Explain how that prevents data bleed. Let's say I'm an AI trying to predict housing prices.
It's a good example. Let's say your data has square footage and number of bedrooms.
Right.
Those two things are highly correlated. If a house has more bedrooms, it usually has more square footage.
Makes sense.
But if you just throw them into a model together, the AI gets confused by the overlap. It's double counting the information.
Ah.
So Gram-Schmidt acts like a mathematical chisel. It takes number of bedrooms, chips away all the information that overlaps with square footage, and isolates only the purely new, independent information.
Oh, wow.
Right. It then plots that pure information at exactly a 90-degree angle to the first variable.
So it's building a scaffold, a numerically stable scaffold where the AI can climb up without the steps crumbling beneath it.
Exactly. Because every new axis is exactly 90 degrees to the previous ones, there's absolutely zero informational interference. Graham-Schmidt is the algorithmic equivalent of looking up at the stars and drawing a straight line to them, creating a new dimension that doesn't interfere with the ground.
That is fascinating.
Oh.
Okay, let's look at the next algorithm. This one connects back to the ancient builders we discussed. The algorithm is called orthogonal projections, or least squares.
Yeah, this is the plumb line.
Okay.
Remember, ancient builders dropped a rock on a string to find the perfect vertical to the Earth.
Right.
In data science, algorithms have to do the exact same thing to find the mathematical best fit when they're trying to map a complex reality down to a simpler model.
And the document uses a great visual here. I imagine a single data point hovering up in 3D space, and the AI needs to cast its shadow perfectly down onto the flat 2D floor below.
Right, so what is the absolute shortest path from that hovering point down to the floor?
It's a straight vertical drop.
Yes, an orthogonal projection. Now, what happens if you drop that line at any angle other than 90 degrees, say at a slant?
Well, the line gets longer. Like, think of a right triangle. The hypotenuse, the slanted side, is always longer than the straight vertical leg.
Exactly. The distance stretches. And in machine learning, that distance represents error.
How?
The longer the line, the more wrong your AI's prediction is.
Yeah.
Any angle other than 90 degrees stretches and expands the error of your model.
Wow.
By dropping an orthogonal line, the mathematical plumb line, the algorithm guarantees the absolute minimum distance, which means the absolute minimum error. It is the optimal approximation of reality.
My mind is blown. The architect's plumb line minimizes physical variance so the building doesn't collapse, and the algorithm's least squares minimizes statistical variance so the AI model doesn't collapse.
You got it.
It's the exact same geometric intuition. Okay, we have one more algorithmic bridge to cross: QR decomposition.
Yes. QR decomposition is arguably one of the most important algorithms in computational math.
Okay.
It's a matrix splitting algorithm. It takes incredibly complex, messy data systems and separates them into two distinct parts, Q and R. Q is an orthogonal matrix.
There's that word again. So Q is doing the same thing the identity matrix does.
Very similar, yeah. Q acts like the perfect isometric foundation we talked about in ancient architecture.
Okay.
Preserves vector length
Yeah.
and prevents any uncontrolled distortion or rounding errors when the computer's crunching millions of numbers. It stabilizes the chaos.
Got it.
But then you have R, and R is what we call an upper triangular matrix.
Okay, I've heard upper triangular matrix described in weird poetic ways before, like it's pointing to the sky or whatever. But mechanically, what does that actually mean for the computer?
Let's strip away the poetry.
Please.
An upper triangular matrix simply means that every number below the main diagonal of the matrix is a zero.
Zero is below the diagonal. Okay, so what does that look like in practice?
It looks like a staircase. And this is vital for computers. Imagine trying to solve a complex system of equations.
Okay.
If I tell you x plus y plus z equals 10, and y plus z equals 6, and z equals 2.
Well, wait, if z is 2, then y has to be 4. And if y and z are 6, x has to be 4.
Boom. You just did back substitution.
Oh.
You solved it effortlessly from the bottom up, step by step, because the bottom of the problem was beautifully simple.
Right.
That's what an upper triangular matrix does.
Okay.
By clearing out all the clutter below the diagonal and turning it into zeros, R creates a clean staircase that allows computers to solve incredibly complex systems lightning fast, working from the bottom up.
So it's not some abstract metaphor about striving for the heavens. It's literally clearing out the noise on the ground floor so the computer can walk up the stairs and solve the problem efficiently.
Exactly. You have the flawless, distortion-free foundation in Q and the highly efficient stair-step structure in R. Together, they allow machines to process reality without getting overwhelmed by chaos.
So when a data scientist sits down today, and types out a few lines of Python to train a massive new AI model using these algorithms, they aren't just crunching arbitrary numbers.
No, they are.
They are literally invoking the biological memory of a toddler learning to balance. They are summoning the architectural instinct of a master mason dropping a plumb line.
They absolutely are. The math works not because humans arbitrarily invented these rules in a vacuum. The math works because it is the fundamental geometry of order in our physical universe.
Right.
An order we evolved to physically feel millions of years before we ever learned to write it down as a formula.
To bring this all together, there's one final profound visual in the source material. It shows a ziggurat, an ancient stepped pyramid from Mesopotamia, sitting right alongside a diagram of a modern neural network, with its input layers, hidden layers, and output layers striving upwards.
Yeah, that image is incredible.
The document calls this the hardware of transcendence. The algorithms powering the future of machine learning are not an alien logic. They are the purest expression of our own deepest biological intuition.
I think that's the most crucial takeaway for anyone listening.
Yeah.
Whether you are a toddler fighting gravity to walk across a living room, an ancient society building a cathedral to reach the sky, or a modern engineer writing linear algebra to train an AI orthogonality, is our universal human blueprint.
Mm.
It is the geometry of stability, it is our biological filter for clarity, and it is our pathway to making sense of a chaotic world.
It really shifts your perspective, doesn't it? Math isn't a chore we have to endure. It's the story of how we learn to stand up.
It really is.
Which brings me to a final thought I want to leave you with today. If our biological instinct for physical balance, our evolutionary proto-math, became the foundational code for artificial intelligence,
Yeah.
as these machine learning models grow infinitely more complex, mapping high-dimensional spaces with thousands of axes that we humans can't even begin to visualize, could they eventually develop their own digital intuition?
Oh, wow.
Are we currently building the inner ear of a future intelligence that will one day create its own retroactive language to explain the universe to us? Something to ponder the next time you find yourself deeply appreciating the clean, 90-degree lines of a well-built room.
Thanks for joining us on this deep dive. Keep seeking clarity in a chaotic world.